Okay, so we have, so this is the question number 3. So we have done that, we have shown that a matrix is in its not in its row echelon form. Okay, so let me once check. Okay, fine. So the matrix, question number 3, matrix A matrix is in its not row echelon form. So now we have to check the column echelon form. So for that we have to look at the first column. So the first column, now it is the first column, it's 1 and right everything in its rights are 0. Okay, so the first column satisfies the condition. Second column, it's also the here is 1 and everything right is are 0, so the second column is also fine. Third column, it's the 1 and everything right to 1 are 0, so it is also satisfy the condition. And the fourth column, everything are 0, so it's also fine. So means, so A is in its column echelon form. Fine. So the second option is correct. And the third option is saying that the matrix A is neither row echelon form nor column echelon form, so it is not correct. So the third option is false. Question number 3 is also done. Now move to the question number 4. Okay, question number 4, what it is saying, that T denotes the set of all permutation matrices in MNR. So what are the permutation matrices? Means these are all set of n cross n matrices which corresponds to the elementary row operation of type 1. What are the type 1 elementary row operations? So these are done in the class. Means take the identity matrix and just interchange the rows. Means in just flip the rows 1, 2 or 3, 4, any ij row you have to interchange. So this is the type 1 elementary row operation, and so T consists of all such and the product of such matrices. So these are called the permutation matrices, and now you have to check which of the following options are correct. So what is T? So T is the set of all permutation matrices. In MNR. Right, so means this kind of matrices are there. So identity, suppose this is IN 1 0 0 0 0 0 1 0 0 0, everything is 0 0 0 0, 1 is here. So this belongs to in T. So now if we interchange the first and second row, what will happen? Suppose this is J. So this is 0 1 0 0 0 0 1 0 0 0 0 0 0 and everything 0 0, here it's 1 0 0 0 0 0, it's 1. So it is also in the T, because this is the interchanging the first and second row R1 2, we are interchanging the row 1 and 2. So this is also in the T. So this kind of matrices are in T. Now you have to show that. So these are basically the elementary matrices, right? And product of elementary matrices. Okay, so let's come to the first option. What it is saying? For A belongs to T, determinant of T, a determinant of A should be 0. Okay. So you have to, so it's saying the first option that if A belongs to T, then what will happen to determinant of A? Is it 0? Means it's saying that is it 0? but you know that elementary, these are the, so elementary matrices are in T, right? So note elementary matrices are in T and the product of elementary matrices, and you know it was done in the class that elementary matrices are invertible, as elementary matrices are invertible. So which imply, so invertible means they have the bijective, right? So it says the rank, so rank should be n, means determinant, so there is a if and only criteria, and also so means date A is non-zero, as we also know date of A is non-zero if and only if A is invertible. So means date of A would not be 0, right? So the first option is false. So date cannot be 0 if A is in T. Now you have to check the next option. It is saying that for A belongs to T, date of A will be equal to 1 or minus 1. So let's check this. So if A belongs to T, then date of A either plus 1 or minus 1, right? So first take the type 1 elementary matrix. So these are T consists of type 1 elementary row operation, right? So these are just the interchanging of rows, right? And you know, if you interchange the rows, then the sign will change, right? So then what happens? So as T consists type 1 elementary matrices, and they are obtained by type 1 elementary row operation type A or elementary row operation from identity matrix, right? So what is the type 1 elementary row matrices? And type 1 elementary row operation are just row operations are just interchanging of rows. Interchanging of rows, and as sign changes, when we interchange rows, so therefore, so identity is there, means determinant of identity, you know. So as I of n is T and date of in is 1. So if j is in T, so it is just obtained from I by elementary row operation, right? So which imply j will be obtained from elementary, just the interchanging rows. So it can have either, if it is just interchanging of row one times, then date of A, So date of j will be minus 1 if so odd number of row interchange. Odd number of times row interchanges, and it will be 1 if even number. Times row interchanges, right? And T also contains the product of the type 1, right? And also notice one thing. Notice that product of permutation matrices are again permutation matrix. Right. So means as T contains the product of them, though means they are again permutation matrix. So which implies if A belongs to T, imply date of A will be plus 1 or minus 1, because they are again the permutation matrices or the type 1 matrices, so which has plus 1 or minus 1 determinant. So the option number 2 is correct. Now check the next option. What is saying? If for A belongs to T, rank of A should be n, right? Let's check option number 3. So what it is saying? For A belongs to T, rank of A is n. So we have done in the first question that what we have done? Oh, we have done earlier in the second question. We have seen that as by 2 determinant of A is non-zero, right? Because it's plus 1 or minus 1. So which imply A is invertible. So means it has nullity is 0. So by rank nullity, its rank is n. Invertible means it says that it's on 2, which imply, and the rank is the dimension of the range space, which imply A is on 2, which implies rank of A is n, right? Because rank means the dimension of the range space, and range is the full Rn, means it's from A is a matrix from it's MNR, means it's a map from as A is in MNR. So A basically you can view as a linear transform from Rn to Rn, right? Corresponding linear transformation A you can view as a linear transform which is map from Rn to Rn, and it is onto means it's the range is the full, so it has a dimension is the n, dimension of the range, so rank of A is n, right? So the option number 3 is also correct. Now let's check the option number 4. What it is saying? If n equals to 2, then for A belongs to T, we have the trace of A is either 0 or 2. So right. So option number 4. If n equals to 2, for A belongs to T, trace of A is either 0 or 2. So for 2 cross 2 matrices, so these are all 2 cross 2 matrices, right? So what are the matrices which are in T? So I2, right? What is I2? 1 0 0 1. This is the identity matrix, it is in T. You can take this J 0 1 1 0. This is also in T, right? So what are the trace of this? Trace of I2, it's 2, right? And trace of J, it's 0. It's the sum of the diagonal, it's 0, right? So we have so these two matrices, if identity and J are in the T, so they have trace 0 and 2, and as the permutation matrices are closed under product, so means as T consists of product of type 1, matrices and product of elementary matrices, permutation matrices are eigen permutation, so they will be of this form, and product of permutation matrices are again, and as product of permutation matrices are again permutation matrices, so they will be of this form, right? I2 or J. So they will be of the form I2 or J, and so which imply if A is in T, imply trace of A is either 2 or 0, right? So for n equals to 2, all the matrices which are in T have the trace either 2 or 0. So the option number 4 is also correct. Okay, now let's check the option number 5. What it is saying, if n is even, then for all A in T, trace of A is even. Okay, so what is the option number 5? Let's check it here. It's saying that if n is even, then for all A in T means in the set of all permutation matrices, trace of A is even. Trace of A is even. It's saying this. We will show that this is false. We will show. So this is false. So we will give a counter example. So let's do it for M4R, means 4 cross 4 matrices. So let's take these matrices. Take A equals to this, A equals to 4 cross 4 matrices. What will take? 1 0 0 0 0 0 0 1 0 1 0 0 and 0 0 0. Oh sorry, this will take 1. So we take these matrices. So this is a permutation matrices. Why this is a permutation matrices? Because we have just interchanged the row 4 and 2, and 4, it will be the 2 row will be goes to 4, and the means it's just you can interchange the rows 2 3 4. Accordingly you can see that this A is in T, because it can be obtained from the identity matrices just interchanging the rows, right? And now what will be the trace of A? Trace of A means it's the sum of the diagonal entries. So what are the diagonal entries? So these are the diagonal, right? So this is the 1, trace of A is 1, right? So here n is even, but the trace is odd, which is odd. So for even, that for if n is even and A belongs to the trace of A may not be even. So the option number 5 is a false. So this is false. Now let's check the option number 6. What it is? Every A in T is in its row echelon form. So this is by the definition, you can easily check. So the option number 6, what it is saying? Every A is in T is in its row echelon form. Right. So what are the matrices in T? As we have described earlier, that T contains the permutation matrices, means the type 1 matrices. Which are type 1? These are the means matrices which are obtained from the identity matrix, just the interchanging of rows. And also we have seen that the permutation matrices are, if you take the product, then product of permutation matrices are again the permutation matrices. So what is row echelon form? So it should be the type 1, as T contains type 1 elementary matrices so which are in row echelon form, right? Which are in row echelon form. And T may also contain the product of type 1, right? T may also contain product of type 1 elementary matrices. As product of two type 1 elementary matrices are as product of elementary type 1 elementary matrices are again type 1 elementary matrices so means they are also in row echelon form, right? Which means they are also is in its row echelon form. So if A belongs to T, then A is in its row echelon form. So the option number 6 is also true. So every A belongs to T is in its row echelon form. So the option number 6 is also true. So the question number 4 is done. Let's move to the question number 5. Okay. What it is saying? Which of the following statements are true? An elementary matrix is an invertible matrices. So these are done in the class. So I have done in the first option. So what means elementary matrices? What are the elementary matrices? You can see it easily that they are invertible, means what are the inverse? First type 1. What are the type 1? It's just interchange the row ij, right? Interchanging the rows ith and j. So what will be the inverse? Inverse will be I r j I, right? Just again interchange the j and I, swap it, then it will be inverse of the matrices, right? So this is for type 1. What will be for type 2? Type 2 are this is the for C non-zero. This is just multiplied by this C by some jth entry. So what will be the inverse of this operation? Just 1 by C, because C is non-zero, just multiply by 1 by C to the jth row. Then this will be the corresponding to the inverse of that elementary matrices. And for type 3, what is type 3? This is take the jth row and suppose just add the C times suppose ith row, right? So this is the type 3 elementary row operation. Then what will be the inverse? You take the jth row and just subtract it by C times Ri. So this will be the inverse of the type 3. So all elementary matrices are invertible, right? So the first option is correct. Elementary matrix is an invertible matrix. Now the next, what it is saying, if the row vectors of the matrix A in MNR are independent, if and only if determinant of A is non-zero, right? If the row vectors are the matrices are independent, then the determinant should be non-zero. So this option is correct. A similar problem was done in the class. There it was done, if the column vectors are independent, then the determinant A is non-zero. So this is similar, right? So what you will do, will just simply take the transpose of the matrix. So what is saying that option number 2, what it is saying, the row vectors R1, R2, Rn of a matrix A belongs to MNR are independent if and only if data is non-zero, right? So what will be the contrapositive? So if you can show the determinant of A is 0 if and only if the row vectors are dependent, so this will be done, right? So enough to show row vectors R1, R2, Rn of the matrix A belongs to MNR, that matrix are dependent if and only det of A is 0, right? So then by contrapositive means if det of A is 0 if and only if rows are independent. Now we will take the transpose. So how to solve this? So we will prove this. And now take the transpose. Take A transpose. Right. So now the rows become the columns and columns become the rows, right? So determinant of what it is saying that. So take the, and as we know, we also know it was done in the class that determinant of A is same as determinant of A transpose, right? If we transpose it, then the determinant remains the same. right? So date A implies 0 if and only if date A transpose is 0. So which implies date of A transpose is 0, and this is if and only if. So this is the A is the matrix, right? A, what is the matrix? So these are the, now these rows become the column of the A transpose. So A transpose, these are the columns R1, R2, Rn, this matrix, right? Now this becomes the column. So these are the columns. Is not invertible, right? Because determinant of A transpose is 0 means this matrix is not invertible. And you know that every matrix corresponding, what is the linear transformation? So if and only the corresponding linear transformation A transpose, which is defined from Rn to Rn by what is the definition? L of A transpose of X is just the A transpose of X, right? This is the definition. Is not invertible, right? So the corresponding linear transformation of the matrix A transpose is not invertible. So the linear transformation is not invertible means the null space is not the zero dimensional. So the null space, nullity of L A transpose is non-zero, right? This is non-zero. So null space is non-zero means this is the vector space, right? Oh, so which is same as null space of L A transpose. This is non-zero. So what are the null space? These are the set of all vectors which sends to the zero vector, right? So means, so null space is 0 means there are non-zero vector, which implies there exist scalars a1 up to an such that these vectors means this is in the null space such that L of A transpose of this vector a1 dot 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 a, it will take to 0, right? Means it is null space is non-zero means there exists this non-zero vector such that this will take to the 0 vector. And what is the meaning of this? L of N transpose is just the A transpose times A1, and A transpose is the column matrix. So which implies, what is the A transpose? Oh, sorry. L of A transpose times A1 dot 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 AN. So this is means this row, right? R1, R2. This is the matrix where these are the columns, and this row A1, A2, AN. So which is the same as A1, R1 plus dot 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 AN, RN. So this is 0, right? Because L of A is 0. So what is the meaning of this? Where AI is these are the non-zero vector, right? So means which implies that R1, R2, Rn are linearly dependent. Right? Because this is 0, where A1, A2, An these are not all 0, which means these vectors, now it is column vectors become for A transpose are linearly dependent. So we have shown this, right? Row vectors are 0 if and only if determinant of A is 0, right? So date of A is 0 if and only if R1, R2, Rn are linearly dependent, right? So it proves that this claim means then the option number 2 is correct. Row vectors of the matrix are independent if and only if data is non-zero. So the option number 2 is correct, right? Now let's come to the option number 3. What it is saying, there exists a matrix in MNR with rank n and the determinant is 0. So can there be a matrix in MNR so that rank of that matrix is n but determinant of A is 0, that matrix is 0? There cannot be, right? Means rank of A is n means it is the invertible, so means determinant should be non-zero, right? So this option is false. So option number 3 means there does not exist any matrix in MNR such that rank of that matrix, any matrix, let's say A, rank of A is n and determinant of A is 0, right? As rank of A is n, which implies if and only if, what is this, nullity of the corresponding linear transformation LA, right? Nullity of the corresponding linear transformation LA is 0. So if and only if the LA is invertible, which imply the corresponding matrix is invertible, means the determinant is non-zero, right? Means the determinant of A is non-zero. So this is false. So the option number 3 is false. There cannot exist a matrix such that rank is n and determinant is 0. So the option number 3 is false. Now what is option number 4? If all the matrices, all the entries of a matrix A is in MNR are non-zero, then the rank of the matrix is non-zero. So let's check this. What it is? Option number 4, saying that if all the entries of a matrix A is in MNR are non-zero, then rank of A is non-zero. So this is correct, right? Suppose this matrix A11 dot 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 A1n dot 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 AN1 dot 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 ANN, and what it is given, all the entries of the matrix are non-zero, means A, Ij all are non-zero for all Ij, right? So means the first rows will always be a non-zero, right? Which imply first row will always be non-zero. So even if the other rows are dependent, we can make it 0 in terms of when you do the reduced form, then at least you will get the one row which is non-zero, which implies, and the rank of, so the rank of A is given in terms of when you do it in reduced form, it is the number of non-zero rows. always be non-zero in its reduced form. So which implies rank of A is always greater than equals to 1, right? Because the first row is always be non-zero, right? So rank of A is always greater than equals to 1. So means the option is correct, option number 4. If all the entries are non-zero, then the rank of A is non-zero. So this is correct. So now let's do the option number 5. What it is saying, if all the entries of the matrix are non-zero, then the determinant A is non-zero. So this is not correct. Rank is non-zero, but determinant may not be non-zero, right? So let's take this example. You can take easily. So let's take A equals to this in 2 cross 2, 1 1 1 1. This belongs to in M2R, and all the entries are non-zero, right? So then what is the determinant? It's 0, right? So the option number 5 is not true. Determinant may be 0 if all the entries are non-zero. So the option number 5 is false. If all the matrices entries of the matrix are non-zero, then determinant may be 0, right? So the question number 5 is done. So let's move to the question number 6. Okay, now what you have to do, you have to compute the rank of the following matrices. So what is the rank of the matrix? So rank of the matrix is if you do it in the row reduced echelon form, then the number of non-zero rows are the rank of the matrix, right? So what we will do, first we will make A in row reduced echelon form, row echelon matrix, row reduced echelon form. Then the number of non-zero rows will be the rank of A, right? Because the rank is not changes when we do the row reduced, right? So this is done proved in the class that rank does not change when we make it row reduced echelon form. So you have to row reduce it, the matrix A. So let's do it. A is given, A is what it is, 3 cross 3 matrices, pi 0 1 1 is square, pi 0 1, right? So what you will do first, so you have to make it 1, first row we have to make it 1, so just interchange the first and second row. So what you will do, first interchanges the 1 and 2, right? Then what it will be, it will be 1 is square, pi, and it will come to the second row, first row pi 0 1, and the last row is as it is, pi 0 1, right? Now what you will do, you will make this the other two entries below the first first row in 1, we have to make it 0. So what we will do, sorry, let's do it in the black. So what we will do, we will multiply the first row by pi and subtract it from 2 and 3. So what you will do, R2 minus pi times R1 and R3 minus also the pi times R1, right? So then what you will get, first row m does not make any changes, so it will remain as it is, 1 square pi. Second row, it will make pi minus pi, it's 0. Here it will, this minus pi times square, so minus pi square. Third row, this will become 1 minus pi square. And the third row, what it will be again 0, because these two are same, so it will be again pi minus square, and it will be 1 minus pi square, right? So first, so the 1 0 0 it will become, now you have to make it the second, this entry to be 1, right? This entry, second row, second column. So for that, what transformation we will do? So this is the type 2 transformation we will do. This is the non-zero element, means what you will do, 1 by minus pi square we will do times R2, right? So then what it will become, it will become 1 square pi, 0, it will become 1, and here it will become pi square minus 1 by pi square, right? And the third row, it is as it is, pi square and 1 minus pi square, right? Now you have to make the other two entries in the second column to be 0. So for that, what we will take the transformation, we will multiply the second row by square and subtract from 1, so we will do R1 minus square times R2 and R3 minus, it will have to add it, pi square times R2. So these two transformation we will do. Then what it will become, so the first, it is 1, it will become 0, if we multiply this by square and subtract it, it will become 0, and now this multiply by this square and subtract it, it will become pi minus pi square minus 1 by pi, right? This second row, it is as it is, 0 1 pi square minus 1 by pi square, and this is 0, you have to, so the second, this entry will be 0 because we have multiplied by pi square and add it. Here again you have multiplied by pi square and add it, then it will become 0, right? If you add it, it will become 0. So we will get this. So now it will become the row reduced form, because the first row it is 1 and everything below is 0. Second row it is 1, everything below is 0. Third row is 0. So now it is in row echelon form. Now what are the number of non-zero rows? These are two non-zero rows, right? So rank of the matrix A is 2. So which implies rank of A is 2, right? So the answer is rank of A is 2. So question number 6 is done. Let's move to the question number 7. Okay, here again you have to find the rank of the matrix. So again you have to make it the row reduced form and then check number of non-zero rows. So let's do it. B one, 2, 0, 0, 0, 1, 2, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 2 3 5 7, right? So what you have to do, the first row it's 1, below everything we have to make it 0, so you have to make it 0. So what we will do, we will make the R4 minus 2 times R1, right? So then what it will become is 1 2 0 0, all other rows remain fixed. So here it will become 0, 3 it is 4, 3 minus 4 it's minus 1, 5 minus 0 it's 5, 7 it's 7. So first row is in its fine. The second row, now you have to make it, it's 1 is already, so you have to make the other 2 entries 0, right? So make the transformation again. So what transformation we will take? R1 minus 2 R2 and R4 plus R2, right? So then what it will become? So we will make R1 minus 2 R2 means it's 1, it's 0, 2 times R2 it's minus 4, it's 0, 0 1 2 0, 0 0 1 1. Here you are just adding these two, R2 and R4 means 0 0 7 7, right? So the second column is also fine. Now the third row, it's 1 is, you have to make the other entries in that column to be 0. So you have to make 3 operations here. What you have to, so R1 plus 4 R3, right? And R2 minus 2 R3 and R4 minus 7 R3. You have to make 3 transformations. So then what it will become? So what, R1 plus 4 R3, add, multiply 4 row 3 by 4 and then add it to 1. So it will become 1 0, it will become 0, if it will become 5, right? Oh no, sorry, 4. Second row, R2 minus 2 R3, so 0 1, R2 minus 2 R3, this will become 0 and this will become minus 2. Third row as it is, and the last row it will become 0 0 till 0, it will be again 0. And now see that this matrix is in its row echelon form. So what will be the, so now it is in its row echelon form, it is in its row echelon form. So the rank of B is the number of non-zero rows in the matrix B. So what are the number of non-zero rows? 1 2 3, and the fourth row is 0, so the rank of B is 3, right? So the rank of B is 3. So question number 7 is also done. Let's move to the question number 8. Okay. A and B are two matrices, M and R means two n cross n matrices. A transpose denotes the transpose of the matrix. So you have to check which of the following statements are true, right? So determinant of A equals to determinant of A transpose. Actually this is done in the class, we have also used it earlier. So in the class it was done for invertible matrices, and for non-invertible matrices not that. So let's do it for, so the first one, in class it was shown that for invertible matrices det of A equals to det of A transpose, right? So this is basically the, by the A, if it is invertible you can write it in terms of product of elementary matrices, and now take the determinant, and the product of determinants it's a split up, means det of A B is det of A into B. Now using this you can prove this. And now if A is not invertible, means det A is 0. If now det A is 0, so this is if and only if A is not invertible. Now the property of A transpose is also will not be invertible, right? Means you can check that the A transpose basically map, if A is a map from Rn to Rn, it will V to W, it will map from W to V, right? No, here it is invertible, means it is mapped from same to same. So A transpose basically will same map. Invertible means it is square matrices. So A transpose will basically the rank will be, range will be A of, range of A will be the domain of A, and the domain of A will be the range of A. So it is also not invertible. And A transpose is not invertible means det of A is 0. A transpose is 0. Right? So basically these two are same. So determinant of A equals to determinant of A transpose, this holds. Now what will be the determinant of CA? If you multiply a matrix by a scalar C, what will be the determinant? So it's saying that it will be C times det A. So this is not true. So why? Let's check it. Suppose take A is a 2 cross 2 matrices 1 0 0 1. What is the determinant of A? Determinant of A is 1, right? Now take a C non-zero. Then what will be the C of A? C of A is multiply all the column by C. C is 0 0, it will be C. Then what will be the determinant of CA? It will be C square, right? So is this equals, and what is the C times det A? It's C. So these two are not equal, which imply determinant of CA is not equals to C times determinant of A, right? So what is actually happening? So you can note that it is because it is 2 cross 2 matrices, determinant of CA is C square times determinant of A, right? Not C times. So note, if A is in MNR, then determinant of CA is the C to the power n times determinant of A. So this will hold. So means this option is not true. Determinant of CA is not C times determinant of A. So option number 2 is false. Now let's check the option number 3. Determinant of A inverse is determinant of A transpose whole inverse. So option number 3. To show what we have to, we will show this is correct. Determinant of A inverse, what it is determinant of A transpose whole inverse, right? So let's check it. So we have as A inverse, you know its identity, right? Now take the transpose, so which implies A inverse whole transpose is again identity, which means A inverse transpose, A transpose is identity, right? And what is the meaning of this? Means A inverse transpose, so A transpose inverse is the, so which is the saying that this is, so suppose this is the matrix B, then this will be the B inverse, right? Because this is identity, which implies A transpose inverse is the A inverse transpose, right? Then therefore, so determinant of A inverse, we have shown earlier the first option by determinant of A inverse transpose, right? By 1, this is by option 1, and which is same as, right, this determinant of A transpose inverse, right? So this is determinant of A inverse is A transpose, determinant of A transpose inverse. So the option number 8 is correct. Option number 3 is correct. Determinant of A inverse, determinant of A transpose inverse. Now option number 4, what it is? So you have to check determinant of BA equals to determinant of AB equals to determinant of A into determinant of B, right? Okay, so in the class it was done that determinant of AB is determinant of A, determinants of B. In class it was done that determinant of AB is determinant of A times determinant of B, right? So then determinant of AB is determinant of A times determinant of B, and these are the numbers, so they will commute, means this you can write determinant of B into determinant of A. So if we again apply, this is the determinant of BA. So determinant of AB is determinant of BA, and which is the same as det A into det B. So the option number 4 is also correct. Determinant of BA equals to determinant of AB equals to det A into det B, right? Now you have to check, now what is the option number 5, fifth? Rank of A is the rank of A transpose, right? So let's check. So option number 5, rank of A is rank of A transpose. This we have to check. So it was done that any matrix A can be written as any matrix A can be written as A equals to, you can write B this will be identity R cross R identity matrices, and 0 matrix of order R cross n minus R, 0 matrix of order so m minus R cross R. So suppose this is a m cross n matrix, right? So let A is a matrix. Where it is the matrix is given? O is in M and R, so it is again n. N minus R cross R, and this is 0 n minus R cross n minus R, right, times C, where B and C are invertible matrices. So this theorem is done in the class. Actually B and C B and C are the product of elementary matrices. Right. So means they are the invertible. Then what will be the rank of A? So you have to find. So just transpose this expression. So if you transpose this expression, what will happen? So then A transpose. So this, if we transpose this expression, it will become C transpose, this whole matrix transpose, and into B transpose, right? So this will become C transpose IR, this is 0, this will become R cross, so this will become R cross n minus 1 R cross n minus R, 0 n minus R cross R, 0 n minus R cross n minus R. Oh, this is the same thing, and B transpose, right? Sorry, this is the transpose. So if you transpose it, it will become this, and again B transpose and C transpose are invertible. B transpose and C transpose are invertible. So A transpose is the C transpose, this matrix, and B transpose, and as B transpose and these are invertible, so rank of, so which implies a rank of A transpose is basically rank of, suppose this is denoted by D, this matrix, then because and as, which imply rank of A transpose will be rank of D. So what is the rank of D? So this is the R, right? Because it's as D is in row echelon form, as D is in its row echelon form, so rank is number of non-zero rows, right? And this has R number non-zero and everything other 0 cross 0 matrix. So this is the rank of R, and A is the again same, right? So from here you can see the rank of A. What is the rank of A? So suppose this is by star, also by star, rank of A is R, right? Because this is the same logic. It has R number non-zero rows and B and C are invertible. So rank of A is also R. So therefore rank of A is equals to rank of A transpose. Right. So as these are both equal to R, so we have shown that rank of A is rank of A transpose. So the option number 5th is also correct. Right. So question number 8 is also done. Okay, now let's move to the question number 9. Okay, what is saying that you have to find the, let A be the matrix, you have to find the determinant of A, right? So suppose this is the matrix, suppose A is what is the formula for determinant? So suppose this A11, A12 dot 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 A1n, Aij, AI1, AI2 dot 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 Aij, AIN dot 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 again AN1 dot 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 ANN. What is the formula for determinant? So corresponding to A11, let's denote the cofactor, means delete the first row and first column. What is the remaining? It's called the cofactor. So the cofactor of A11 is, we denote it by A11 tilde. So it is the matrix A. You have to delete the first row and first column, whatever remain is the cofactor. So it is the 2 2 A23 dot 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 A2n. Here it will be AN2 dot 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 ANN. So this is the n minus 1 cross n minus 1 matrix, right? So like for any element, for general element Aij, cofactor of Aij, sorry, let's denote it by Aij tilde, right? Then the determinant of A, what is the determinant? So first, so this is the n minus 1 cross matrices, right? And you know the for the 1 cross n matrices, its determinant is the same. And for, so this is by the induction. So this, for matrices we make it, so let me write out them, then let me explain. So with respect to any rows, you have to expand it. So let's j equals to 1 to n minus 1 to the power I plus j Aij, determinant of Aij tilde. So this is the definition of determinant, where data is, this is n cross n matrix, and here the determinant, it's the n minus 1 cross n minus 1, and you know the value for this n minus 1. So by induction you are computing the determinant. So what is this? So for n equals to 1, date of A is the number C. Suppose A is C, date of A is this C. For n equals to 2, so determinant of A, suppose A is this A, B, C, D. What you will take? A, you will take the cofactor of A is D, right? Cofactor of A is D, minus, if you do it, you will get B, and the cofactor of B is C. So this is the for n equals to 0. By induction, this will be the formula. You can check. Oh, this was also done in the class, that this is the formula for determinant. So using this, we will compute the determinant of the matrix this. Right. So as A, what it is given? 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the matrix. You have to find the determinant. So therefore det of A will be, what will be the, so we will, with respect to the first row, we will do, we will expand with respect to first row, right? Then what will become? A and the determinant of the cofactor. So this is 1 1, so minus 1 to the power 1 plus 1, it's 2. So just write it, 1 plus 1 1 into determinant of the cofactor 5 6 8 9, right? Now plus what will be this 2 minus 1 to the power 1 plus first row second column, it's 2 times determinant of 4 6 7 9, right? Plus minus 1 to the power 1 plus 3 into 3 into determinant of 4 5 7 8. So this we have to compute. Well, let me write it again here. So basically det of A will get, so minus 1 to the power 1 plus 1, it's plus 1 into this. So this will get 1 into determinant of, cofactor is this 5 6 8 9. For the, this is the minus 1 to the power 1 plus 2, it's odd, so minus will come, minus 2 into determinant of, it's 4 6 7 9, right? 4 6 7 9. The third, it will be plus minus 1 to the 1 plus 3 3 times determinant of 4 5 7 8. So now compute it, 1 into determinant. What is the determinant for 2 cross 2? You know, this cross multiplies, 5 into 9 minus 8 into 6. So this is 45 minus 48 minus 2 into 36 minus 42 plus 3 into 32 minus 35. Let's compute it. It is the minus 3. Now it is 4 6 plus 12 3 3 9 minus 9, right? If you add up, you will get 0. So the determinant of A is 0. So this is the determinant of A is 0. So the answer to the question number 9 is 0. Right. So question number 9 is done. Let's move to the question number 10. Okay. A matrix is given, then you have to find the 3-2th entry of the matrix A inverse. So if a matrix is given, how to find the inverse? So you have to first check that this is invertible, right? So as it's saying that you have to find the inverse, means the matrix is invertible. So as A invertible, so as A is invertible, which implies A can be written as product of elementary matrices, right? E1, E2 dot 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 Ek for some k, right? So this is the theorem that any invertible matrices can be written as product of elementary matrices, where EIs are elementary matrices. Okay, so now from here we have to find the inverse. So how to find the inverse? So what you will do, because and elementary matrices are invertible and EIs are invertible, right? Because these are elementary matrices, we have done that these are invertible. So just multiply by inverse of this. So then what will happen? So first multiply left by E1 inverse, then what you will get? So you will get E1 inverse A equals to E1 inverse E1 E2 dot 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 Ek. So means this is the what you will get. E1 inverse A is E2 E3 dot 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 Ek. So by similarly multiply just by now E2 inverse E3 inverse, then what you will get? That Ek inverse Ek minus 1 inverse dot 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 E2 inverse E1 inverse into A equals to this side it will be identity matrix, right? Now what will be then A inverse? Now multiply by A inverse, right? As A is invertible, then what will happen? So therefore Ek inverse Ek minus 1 inverse dot 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 E2 inverse E1 inverse will be A inverse, right? So A inverse will be product of the again the inverse of the elementary matrices, Ek inverse Ek minus 1 inverse. So what will happen? So here this you can view as this times I, right? So just so what can you say about this? So if you means, so let's write it in this. So here if you changes the from A, if you apply the elementary row operation, if you get the I, so now if you apply the inverse of elementary operation to I, you will get the A inverse, right? So A you have got, suppose these are the elementary row operation, from A you are applying, what I am saying. So from here you can see. So if you apply the elementary operation, the inverse of the what, if A can be written as like this, product of elementary matrices, then if you apply the inverse of this to I, you will get the A inverse, right? So we will follow these techniques. So let me explain how to do that. So just write A here first. So this is you have to find the inverse of this pi 0 1 1 pi 1 1 0 1, and write this side the identity matrix 1 0 0 0 1 0 0 0 1. Now you will apply the elementary operation over A and we make it the identity, and correspondingly you will make the same elementary row operation to I, and what will be the final matrix? It will be the A inverse, right? If you apply the same elementary row, because if you apply the that same inverse in order to make it I. The same operation will make I to A inverse, right? So these two by these two, you can see, right? So we'll make it this side to be identity, and we whatever it will be in the final stage, it will be the inverse. So let's do, we'll make it into row reduced form. So first row you have to make it 1. So just interchange this row 1 and 3. What you will do, R13, and what it will become? It will become 1 0 1 1 pi 1 pi 0 1. So similarly you have to apply it here. So then this will become 0 0 1 0 1 0 1 0 0, right? Now you have to make these two entries to be 0. So for that, what you will do, you will just subtract R2 R1 from R2, and R3 you will do minus pi times R1, right? So do this, then it will be 1 0 1, it will become 0, it will become pi, it will become 0. The third row it will become 0 0, it will become 1 minus pi, and this side what it will become, R2 minus R1. So R1 is, there is no changes. In R2 0, you have to make it 1, and it will be minus 1. Now R3 minus pi R1 1 0, this will be minus pi, right? So first column in its row echelon form. Now again we have to make the second entry, means second row second column entry to be 1. So what you will do, will 1 by pi will do times R2, right? Sorry, then what it will be, it will be 1 0 1 0 1 0 0 0 1 minus pi. The correspondingly here what it will be, 0 0 1 0 1 by pi minus 1 by pi, it will be 1 0 minus pi, right? Now you have to make this entry to be 1. So then what you will do, so divided by 1 minus pi, 1 by 1 minus pi, R3, and it will become 1 0 1 0 1 0 0 0 1, and this side it will become 0 0 1 0 1 by pi minus 1 by pi. You have divided by 1 minus pi, 0 minus pi by 1 minus pi, right? So you have to now make it this to be 0 to make it identity. So now you will do R1 minus R3. R1 minus R3. Then it will become 1 0 0 0 1 0 0 0 1, and this side what it will become, R1 minus R3 so this will now become r1 minus r3 means 1 by 1 minus pi, it's 0. It is 1 minus this, so 1 minus this means, so just write it 1 plus pi by 1 minus pi. Nothing is changes. 0, 1 by pi minus 1 by pi, 1 by 1 minus pi, 0 minus pi by 1 minus pi, right? So this side it will become identity. Now this is the identity, so this will be the A inverse, right? So what is the inverse? So A inverse is this. Minus 1 by 1 minus pi, zero. If you do it 1 minus pi, it's 1 by 1 minus pi, 0, 1 by pi minus 1 by pi, 1 by 1 minus pi, 0 minus pi by 1 minus pi, right? So we have got the A inverse. Now let's see what we have to find. We have to find the 3-2th entry, the third row, second column. So this is the third row, second column. So 3-2 entry is 0, right? So 3-2th entry of A inverse is 0. So the answer is 0. So the 3-2th entry of A inverse is 0. So this is the, so question number 10 is done. Okay, so this was the last question. So this finishes the assignment 6. Okay. Any doubt? So if no, then let's stop for today. We'll meet in the next week. Okay, bye then. Let me stop the recording.